Alright, so today we're going to get into some technical details for the feed-forward neural nets. And so our notation, it's going to be fairly notation heavy, so bear with me, and you may need to watch this a few times. There is a lot of notation here. But before we get into new material, let's just review what we've done so far. And the book or the videos don't make this as clear as I'd like to see it. But when we were talking about a neural net, now we're just doing a three-layer. Uh, the neural network is composed of a series of mappings, right? Oops, and I got the labels wrong here. So it's a mapping first from Rn to Rk, and then it's a mapping from Rk to Rm, and this is an N by or NKM network. Okay, and so we're just mapping Rn to Rm through Rk as an intermediary. Okay, so when we're talking about this network, I think it's best to visualize it as, you first take your x, and then what do you do with x? Well, this first mapping from Rn to Rk, first there's a linear part, and that's the pre-state. So the pre-state takes in x and maps it to Rk through matrix W, 1. Okay, and then we add on the affine part. Okay, and then the key part of this to make it nonlinear is the state value, which is applying the activation function to that. Okay, and that's it so far. This is these are the, you can think of this as a vector in Rk, right? And so this has the state nodes or state values of each node in the hidden layer. And then we take that value and we take the next pre-state, which is just W2 times our middle state plus P2. And now we could apply a mapping to this, but typically we don't. Yeah, so typically we would just say S2 is equal to P2 for that one. Good. And so this is our output. Of the neural net. This is our input. Okay, so you could do these series of steps without the network structure, right? You could just use the linear algebra to do this. And we're actually going to do that when we construct our own neural net. Okay? Okay, so this notation, the network notation, is really there to help us keep track of what's going on. So by that I mean the following. So where is the weight, Wijl, in the graph? What is it connecting? Well, it's an edge between two weights, right? And so this would be Wijl. And so it's connecting node. Which node is which? Yeah, this is node J. And this would be node I. And this would be layer L. That's the layer L. And layer L minus 1. Okay, now where in node I, where in the computations that we're performing in node I, right, where does this particular weight come into play? Well, remember the computations that we're making on node I. First we take the pre-state. So pre-state of node I, that's the elf layer, and this is node I, is going to be W L times S L minus 1 in vector form, right? Plus B L. Okay, but I wanted to identify Wijl, right? So how would I do that? Well, one way to do that is to think of this as WIJL times what part of S? Well, if I look over here, right, this is just going to be the jth node of layer L minus 1. That's the only one that this is going to touch, right? So this is just going to be SJ L minus 1 plus a bunch of other stuff, right? And so this is the only spot where WIJL is going to appear in this pre-state computation, right? And I say that because we're going to be taking the derivative with respect to this, and so it's going to be important to identify how this is related in this mess here, in this matrix multiplication. Okay, so we'll come back to that in just a minute. But it's good to keep this notation in mind because we're going to be looking at a lot of notation here. Good. So now that we've covered our notation a little bit, kind of an overview as to how I think of these neural nets is I think of the node as a computational node, and in that computational node I'm thinking of storage. So I'm thinking when I go through the forward pass, I'm going to store my value of the pre-state, and we've talked about how to compute the pre-state, right? You go ahead and save storage for the state, and then go ahead and save some storage for the S prime while we're at it. And there's one other storage place that we need to keep in a node, and that is a delta. And my goal is to compute these deltas with you today, and to show you how these deltas relate to the gradient of the error. Okay, so there's four pieces of information on each node. Good. And so again, we already know how to compute the pre-state on the node, the state on the node. The derivative is just what you think it is. It's the derivative. What you could say is, S prime is equal to sigma prime of P, whatever the P value is. And so the only thing that we don't know when we take the forward pass is the value of the delta. We'll fill in the other three values. And so those numbers are going to be there for us when we go to compute the deltas. Okay, good. All right. So computing deltas in the network. The backwards pass. We're going to be going backwards. Okay, so on the last layer of the net is layer L. And what's being output here are the Y's, right? And so I'm going to go ahead and define delta as a vector here is going to be the vector of the targets. Oops, well, whatever index of the target I'm working on. Notice that this is just one data point at a time. We're kind of thinking of, we're going to be using stochastic gradient descent, so we're just going to need to do this on one data point. If you wanted to use more data points, you could, but we'll just do one. Okay, so we're going to define delta this way, and so therefore delta has now been computed on the output layer. And now we want to figure out how to compute delta on the other layers. And so the way to think about that is we're going to have some inputs here. And so this is going to be like delta 1 of layer L plus 1, delta 2 of L plus 2, L plus 1. That's, we don't move the layers around there. There we go. And so this is W what and W what and W what. Well, let's call this node K in layer L, and then what would the W's be then? Well, this is going from K to 1, and then from K to 2, and then from K to 3, right? So I'm writing those in reverse. Good. And then there's something going on right here, and that's where the delta is being computed. So our delta for node K in layer L is going to be S prime. Well, missing my index there. SLK prime times the sum, and now we are working backwards. We're going to take this delta times this weight, and this delta times this weight, and this delta times this weight. And so we will just have j equals 1 to k, or 1 to 3 in this case. But this would normally be the number of nodes in layer L plus 1 times delta j L plus 1 times w j k L, right. Oops, sorry, that's those are L plus 1s. The way I've defined the weights. You know, like W1 is before layer 1. And so this is like the input layer. Input layer is layer 0. Yeah, okay. And so, is there a way I can do this without having to do an individual computation? Can I do this using matrix form? By the way, if you were actually computing these, if you were, one way to do a neural network, right, is to attach a bunch of computational nodes together. So if you were doing that, you may want to keep the individual computations going, so you can just compute the 4 values on each node as you go, right? But since we're going to be using linear algebra to do this, we'd like to get the matrix version. And so I'm going to stop here, and in the next video we'll talk about how to write the deltas using linear algebra.